If we want to look at the rows of a matrix as vectors. Then, when we do row operations, it's equivalent to doing the same operations to vectors. And we want to talk about the linear independence of the rows. Linear dependence or independence of the rows. Very important idea. Okay, so what I want to say is that the rows of the matrix are linearly independent if the reduced matrix, completely reduced matrix, the Jordan form and so forth, has no rows of zeros. Okay? And that's because multiplying a row by number, adding multiples of rows, or switching rows doesn't affect their linear independence. If you think of linear independence as no vector is sum of multiples of the others in the set, so we'd be saying that no row is a sum of multiples of others in the matrix. Then if this row isn't a sum of multiples of any of all the others, then neither is a multiple of this row. Neither is 5 times this row. Okay, if it was, then you take 1/5 of whatever multiple adds up to this of the other rows, and that's a multiple of the other rows that add up to this one. Adding multiples of rows doesn't affect the linear independence of rows. I don't even want to say it, but think about what it means. Switching two rows doesn't affect the linear independence of the rows. Okay, so if you start out with linearly independent rows, you're going to end up with linear independent rows. Conversely, if you end up not conversely, but if you end up with a row of zeros, well, that means some row was a sum of multiples of the others because you had to use a sum of multiples of the others to get that row down to 0. Okay? So we let the statement stand. I'm not going to prove it just for sake of time. You can read it in the book, but it's a fairly simple idea. Okay? Now, accepting that this is the case, well, let's say we reduced some matrix, okay, and we got the matrix we have here. Then this tells me that the original rows were linearly independent because we don't get a row of zeros. And we can see, in fact, that since all these rows were sums of multiples of original rows, or obtained by switching some of the rows, that these three rows span the same space that the original rows did. Now, we can clearly see that these rows are linearly independent. For example, I've got a 1 in the first row and zeros. I've got a 1 as the first number in the first row, and the other rows have just zeros. Okay, so there's no way that adding non-zero multiples of to the second and third row is going to give you anything that's equal to the first row. Okay. Similarly, for the second row, we've got a 1 here and zeros above and below it. There's no way that multiples of the first and third row can give you something that adds up to -1 or adds up to 1. Okay, so that these two rows, multiples of these two rows can't possibly add up to this one. And similarly for this one. Multiples of these two rows can't possibly give you 1 here because all you've got is zeros. So that shows that these rows are linearly independent. Also, they span the same subspace. Okay, these rows are all linear combinations of the original rows, and therefore they span the same subspace. Now again, I haven't proven that. It's something that needs to be proved, but it's something you can rely on, okay? Also, we can say that, well, we have leading ones here, here, and here. You know, leading one is the one in a row where there's nothing but zeros to the left. So clearly that's a leading one. This is a leading one because nothing but zeros to its left. Same with this one. Then these three columns, columns 1, 3, and 5, the columns that contain the leading ones from the rows, in the first place are linearly independent, but more importantly, the original columns 1, 3, and 5, the columns corresponding to the columns with the leading ones in the original matrix are a basis for the column space. And remember, the column space is the space of all vectors that you can get by multiplying this matrix by compatible vectors. Okay, now compatible vectors here would be vectors in R5, right? So, because you have to have 5 elements in the column to match the 5 elements in the row, so you have vectors in R5, multiply them by this matrix, and you get vectors in R3, because there are only 3 rows, and each row gives you a row of the new matrix, okay? Again, this tells you then that all the vectors that you can get by multiplying this matrix by columns of 5 vectors, in the first place they're in R3, in the second place, the first, third, and fifth columns of the original matrix form a basis for that space. Now, of course, that space is all of R3, so that's not, in this case, an overly useful result, at least not as useful as it would be if you had a different, if you had a row of zeros in this matrix, okay? And we'll see what I mean by that in a minute. The main point here is, if you reduce the matrix, the rows that you end up with span the same space as the rows of the original matrix. And also, the leading ones give you the columns, which in the original matrix give you the column space. Okay, so we'll see what happens now. Well, what if the reduced matrix was this? We do have a row of zeros. Okay, well, let me come back to that question.